Welcome to Chemistry at Hananiga High School. I'm Brian Brown, and today we'll be looking at our Day 5 set of notes dealing with quantum theory and the electron. Now, we've been looking at how we had been slowly building and inching closer to a true understanding of the position and the energy of electrons. And that brings us to the Schrodinger's wave equation. We just looked at how Heisenberg had said, you're looking for something you can't find, both the precise position and precise energy of the electron. Well, what happened was, rather than wasting time trying to disprove him, some scientists tried to work around, and Schrodinger's wave equation provided scientists with a way to do just that, overcome Heisenberg's dilemma. Because what he recognized was, if I want precise information about energy, like trying to get a letter to you, I don't need to know where you're at all of the time. If I send it to your house, you're going to be there a lot of the time, and that should be good enough to know your position. So he said, as if we want precise information about an energy, we have to live with uncertainty in electron position. So he basically, through his wave equation, is able to predict at precise energy amounts where the electron is at 90% of the time. And yes, that means in precise location information, but that three-dimensional region of space his wave equations predict is a good enough approximation of the positions of the electrons. So he got around the dilemma presented by Heisenberg. So unlike Bohr's model, Schrodinger's new model for the hydrogen atom seemed to apply equally well to all atoms of all elements. And this was a huge step forward. No longer did it only work for hydrogen, it worked for everything. So with this equation, modern quantum mechanics was born. Now, in the quantum mechanical model, we have a whole bunch of scientists that over time have contributed to our understanding of the electron. Now, what we're looking at in this picture here is a snapshot of the electron's position over a whole series of snapshots. So if you take, every second we look at where the electron is, and then do that for, 1,000 seconds, and then superimpose those images on top of each other, we get a visualization of where the electron lives. It's called the electron cloud, and this represents the electron probability, where the electron is at most of its time. Now, in quantum mechanics, we look at electron position as energy as being described using energy levels, Bohr idea, energy sublevels, and that allows us to understand everything past a one electron atom, orbital shapes, and spin. So we really have 4 bits of quantum information we typically look at when we're talking about electrons inside the atom. Now, that probability cloud you see up there, that dot in the center, that would represent our nucleus. I know it's not drawn to scale, it should be significantly smaller. And that red area is our probability cloud, our electron cloud. And what we basically do is we can draw a picture and say 90% of the time the electron is inside here. So we're not talking about where the electron is all the time, but we can see in 2 dimensions this would be round, but in 3 dimensions this would be a spherical shape. We can see where the electron inside hydrogen is at 90% of its time, 90% of its life. So it gives us good enough information about position to the precise level of energy that we need. Now, there is a quantum mechanics movie that I want you to watch. So pause here, and at the end you'll notice there is a link dealing with levels and sublevels. So it gets into a little bit deeper what we're going to be looking at. So it sets up the ideas that we're going to be talking about in the next few slides. So pause here, go back, take a look at that, and then come back. Now, looking at the different bits of quantum information. First, we have the principal energy level. Sometimes it's called just the energy level. The symbol for the energy level is N, and it's referred to as the first quantum number, or the principal quantum number. It just means what energy level are the electrons that we're studying on. Now, the energy level describes distance from the nucleus and general energy. So while we can't say that energy level 3 is always lower in energy than energy level 4, so to speak, we can say that the average distance from the nucleus that an electron in the 3rd energy level is at is going to be closer to the nucleus than the average distance from the nucleus that a 4th level electron is at. So it describes the distance from the nucleus, which is very important in many different situations in chemistry, and it deals with general energy. And we'll get to a second why it's only general energy. Now, we have basically an infinite number of energy levels, but we tend to look at the first 7. So we talk about n equals 1 through 7, meaning the first 7 energy levels inside an atom. And remember, the higher the energy level, the greater the average distance from the nucleus. Now, each energy level contains sublevels. Once we get more electrons than one inside an atom, so anything beyond hydrogen, our energy levels sometimes split into energy sublevels. And that's why it's a little bit more complex than what Bohr was looking at. Now, the number of sublevels on a level is equal to the energy level. So if n equals 1, the first energy level, I only have one sublevel. So there aren't multiple sublevels on the first energy level. There's just one. But on the second energy level, I have to have two sublevels. And on the third, we would have three. And technically, yes, on the ninth, we would have nine. Although we really only have enough electrons to worry about in ground state conditions about four different sublevels. So we'll end up talking about four different sublevels. So remember, if it's the first energy level, you got one sublevel. If it's the second, you've got two. If it's the third, you've got three, and so on. Now, each sublevel contains orbitals. Now, an orbital is basically the representation you saw with those red dots on the previous picture. It's a probability density of where in 3D space of where the other electron is going to live up to 90% of its life. So orbitals are like our apartments for electrons, and every apartment can hold up to 2 electrons. So an orbital is a three-dimensional region around the nucleus in which an electron moves and is found 90% of the time. And remember, it's an actual physical three-dimensional representation. And the center, we have the nucleus. Now, each orbital can hold up to 2 electrons and only 2. Now, other electrons can move through that region of space, but they're not going to be stuck in that region of space 90% of the time. So electrons visit each other in each other's orbitals all the time, but remember, 90% of their lives, they're going to be in a very specific region of space that can only be defined by 2 different electrons. So only 2 electrons per orbital. So our apartments can only hold 2 electrons 90% of the time. Other people can visit, but they're not going to live there 90% of their lives. Now, the total number of orbitals on a level is also equal to n. Or I should say, is related to n, to be more specific. It actually equals n squared. So on the first energy level, we would have a very specific number of orbitals. On the second, we would have more. On the third, we would have more. And that equation, n squared, can give it to us. So each sublevel has a different shape of orbital. So when we talk about sublevel, we're usually giving a symbol, S, P, D, or F. So these are the symbols we use to represent these different energy sublevels. And on these sublevels, or I should say within these sublevels, we have orbitals. And on the entire energy level, if we square the level, that tells us how many of these different types of S, P, D, and F orbitals we have. So there's a very specific relationship that exists between all of these different substances. Now, step back a second. I started to say this and I didn't, so I want to review it. Let's say we're on energy level 1. Well, that means we have one sublevel and 1 squared orbitals. So that's just going to be 1. So on the first energy level, all we have is 1 orbital, and that's it. But when we go to the second energy level, we now have 2 different sublevels. So our level has split into 2 different levels. And 2 squared would be 4. We have to have a total of 4 orbitals on that second energy level. So if we know what energy level we are on, we know how many orbitals. And I'll often represent orbitals as these little dashes. So on the second floor, that's what we're going to see. We have a total of 4 different orbitals. And these different orbitals represent different shapes, which are represented by our sublevels. So let's kind of walk through that idea with our different S, P, D, and F. Now, the first type of orbital we're going to look at is the s orbital, and it's actually a spherical region of space. Each level has one S-shaped or spherical sublevel. So the first energy level has a 1s orbital. So 2 electrons can live in this region of space. Now, we only have one orientation of that s, which basically means on the first floor we have one s orbital, one s apartment, and that's it. Only a single s apartment. Now, how come we only have one orientation? Now, remember, each region of space has to be unique. So if you take a sphere, like a globe, and its center in that sphere would be the nucleus, if you try and spin it, you never occupy a different region of space. It's always the exact same region of space, no matter how you would spin that perfect spherical shape. That's why there's only one orientation of s on every sublevel. So that means an s sublevel can only hold 2 electrons. Once we've put 2 electrons in the 1s orbital, it's full. And any other electrons would have to go to a different orbital. Now, what's different between the s orbitals on each level? Well, they're a larger and larger and larger region of space. So you can see the 2s is larger than the 1s, and the 3s is larger than each of them. But remember, the center of each of these spheres is the nucleus. So the 2s is actually inside the 3s, and the 1s is inside both of them because the center of them is all the nucleus. So remember, electrons in the 3s orbital can visit the 1s orbital all the time, but they won't be in that region of space 90% of their lives. They will be inside and visiting the 1s electrons somewhere less than 90%. They'll also visit the 2s orbital, but they won't be in there 90% of their life either. They'll be in this larger volume of space, the 3s orbital, 90% of their lives. Now, that's the s orbital. So every energy level has an s orbital, and there's only one orientation of s. Now, the p orbital is the second one we're going to look at, and that's kind of a dumbbell shape. I know when you look at this image here, you see it orbiting around the center, which is this nucleus, and you see the 2 lobes. That's just one orbital. So this can hold 2 electrons. So can this one, and so can this one. So when we talk about p orbitals, we're going to see p orbitals on the second energy level and any energy level above. So the second, the third, the fourth, and the fifth all have a p sublevel that look like these barbells. Now, how come we get 3 orientations of the p? Well, picture this as a 3-dimensional space. I could orientate my dumbbell on the x-axis. I could orient it on the y-axis. And if I go to the 3rd dimension, which is hard for me to draw in 2 dimensions here, coming straight out at you, we have a 3rd unique region of space. But once we have 3 different orientations, we don't have any unique regions of space anymore. So that means the p sublevel can hold up to a total of 6 electrons. So when we look at the second level p's, there's actually, oops, drew those lines too close together there. So when we look at our second level p's, we actually have 3 p orbitals, all at the exact same energy. So we've got 3 of them, and each of them can hold 2 electrons. And that's why we often talk about them as the px, the py, and the pz to differentiate between the 3 different orbitals. So the s we only had 1, but the p we have 3 orbitals on the 2p sublevel. So we would end up with a total of 6 electrons. Now, just like the s orbitals, the 3p sublevel, which would also contain 3 different orbitals at equal energy, are all larger in volume than the 2p. So what's different? Well, the only difference is it's a larger region of space. But remember, the center is still the nucleus. And we have basically a region of space where up to 2 electrons can live. So remember, s orbital, every floor, every energy level has an s apartment or s orbital. And on the second floor and above, we also have p orbitals. Now, when we get to the 3rd energy level, we have to have 3 different types of orbitals. And our 3rd type would be the d orbital. And these start to look pretty funky. So the 3rd energy level and above each have a d sublevel. And there's 5 different orientations of a d. So we have 1s, 3p's, 5d's, a very patterned and organized arrangement again. So it would take a total of 10 electrons to fill the entire d sublevel. So on the 3rd floor, we have a 3D sublevel. And there's not one, there's 1, 2, 3, 4, 5. So on this sublevel, we have a total of 5 orbitals or 5 apartments. So that's why it would take 10 electrons to fill. Now, beyond the Ds, when we go to the 4th floor, we have to have a 4th type of orbital, and that would be the f orbital. And now they get really goofy looking. So in the 4th energy level and above, we always have an f sublevel. And 1s, 3p's, 5d's, 7 f's is how it works. So there's 7 orientations of f on a sublevel. And remember, the first time we're going to see an f is the 4th energy level. So we can have a 4f sublevel. It would have 1, 2, 3, 4, 5, 6, 7 4f's. So it would take a total of 14 electrons to fill an entire f sublevel. And that's basically what I wanted to look at today. So it's going to take some time to digest this. So we'll pick it up and look at this even deeper tomorrow. So that ends our notes.